Okay, hello everybody. Welcome to the IRDR Taster Lecture series. Let me first share my screen. All right, and make it full. I'll park it here. Okay, hello everybody. Welcome again. Welcome to the virtual lecture on global water risks and resilience under climate change. My name is Mohammad Shamsudduha. You can call me Shams. I'm an associate professor in humanitarian science at the Institute for Risk and Disaster Reduction, UCL IRDR for short. At the Institute, I lead the IRDR's new BSc program in Global Humanitarian Studies, which we are starting this year for the first time. I also teach on IRDR MSc programs, particularly on um, natural hazard and vulnerability risk module in the IRDR MSc programs. So the idea of today's lecture is to give you a kind of flavor, if you like, what type of uh, teaching techniques and materials we use, especially to teach our MSc students at IRDR. So here I am with one of the topics that may be of your interest. Um, so I'm going to start by reading out the learning outcomes. So hopefully by the end of this lecture, you'll be able to demonstrate knowledge about recent natural hazard induced disasters across the world that are um, perceived or argued to be linked to climate extremes, understanding the relationship between extreme weather events and climate change, and then apply the concept of hazard risks to analyze and assess society's vulnerability to disasters. And also, hopefully, you can learn about the risks and resilience of global freshwater resources, particularly groundwater, to climate change. As by background, I'm a geoscientist with a um, special interest in water resources, freshwater resources, particularly groundwater resources. Um, so these are the learning outcomes, and let me go ahead to the lecture outline. So hopefully I will be talking to you for about 35 minutes. Sometimes I digress, so it could be even 40 minutes. And then hopefully towards the end of the hour, you can ask me any questions if you like by unmuting yourself or perhaps even showing yourself on Zoom, but it's entirely up to you how you want to do it. You can also use the chat box to populate your question as I go along, and then I will pick out the questions towards the end of my lecture and perhaps start a discussion if there is time, and of course if there is interactions from you. So in the first part, so hopefully in the sort of first few minutes, I will be talking about natural hazards, particularly hydrological hazards, and the related recent disasters and the global trend in natural hazard disasters. And then in part two, I'll be looking at, so part one is basically setting the scene. So basically featuring recent hazard events across the world. And then in part two, focusing a bit more on the theory. Since this is a lecture, there should be some theoretical aspects to the lecture. and this is where I'll be talking about the concept of um, hazard risk and how do we assess hazard risk in the context of real world disaster scenario. And I'll also be spending a few minutes talking about the attribution to climate change. We all know climate change is happening, and it is primarily anthropogenic. So there is more and more confidence in the notion of anthropogenic climate change. But often um, we get perhaps carried away too much, or perhaps not very sure how to attribute extreme events to climate change. So there will be some um, aspects of that debate as well in the lecture. And then in the third part, it's towards the end of my lecture, I'll be talking about the links between climate extremes, particularly floods and associated water risks, and on a kind of positive note about the links between extremes, climate extremes, and water resilience. And in particular, I'll be giving an example of groundwater and how groundwater resilience is perhaps linked to extreme climate events. So there is plenty for you to take on, and I appreciate it's perhaps too much of ideas. So I'll try to keep it as perhaps as simple as possible so you can understand. And then perhaps towards the end, we can have some time for a lively discussion. So without further ado, let's dig in. So I'll start with this global map that shows, um, let me get this out of my way. Okay, so I'm showing you this map that I borrowed from the New York Times newspaper, and that was um, published, I think, a couple of months ago, and that was developed by a climate risk data company called the 427. Now, uh, I found this map really interesting. Do I take it as 100% to be accurate? Probably not, but again, let's take it as at the face value and show it, because it's a nice way to kind of um, tell people, regardless whatever their background is. So kind of general people, as newspapers often do, they produce lovely colorful maps to show various things. So anyways, so this map in particular is actually showing at a global scale what are the primary climate risks that the world is going to see going forward in 2040. And in this lovely colorful map, you can clearly see that much of the northern part of the world, the northern hemisphere, you can see it's blue, so the flood is the primary hazard. And then there is also hurricane hazard in some parts of the world, especially in the east coast of the United States. And also if you go towards China and Japan and Korea, there is a high risk of hurricanes. And then if you move towards the center of the world here in Africa, you can clearly see it. There are areas where the flood is the key climate risk, but equally there are other areas, such as in brick red color, you have the wildfire. Now we're very familiar with the wildfires happening mostly in California, but also recently we have seen devastating wildfire in Turkey and Greece as well. So there is also here in the African continent, you can see the risk of wildfire as well as drought and extreme heat that we have seen recently in the North American continent. So this is just to set the scene that on a global scale, what are the primary climate risks we are seeing now, and also we are going to see going forward into the future. So let me just then go into the next slide just to show about the global trends in disasters, particularly in natural hazard induced disasters. And this graph here on the top left is showing long-term trends in natural hazard induced disasters that observed across the whole world. And you can see that the number of various different types of natural hazard and related disasters, such as you can see in different colors. So the red color indicates drought being the hazard, and then green indicates earthquake and so forth, blue being flood. And you can clearly see that since the 1950s to recent time, there has been a sharp increase in the number of disasters until perhaps 2000, and there is a slight sort of decline, or in some parts for some of the hazards, it's not really increasing very much. So there is a sort of break, if you like, in the trend. Now, I'm not gonna try to explain why this is, whether it's due to climate change or other factors. That's not the key point here. The point I'm trying to make here is that although the number of hazard related disasters increased dramatically over time, um, you can see in the black line here, which is superimposed, that actually shows the number of deaths, number of fatalities. Now, of course, every death is a tragic loss of human life, but you can clearly see that the number of death has dramatically decreased over time. So there is a sort of inverse relationship between the number of disasters and the number of fatalities or death, human loss of life we have seen across the whole world. What is interesting though here is that the number of extreme weather events, so which is shown in this light yellow color, you can see that the number of extreme weather events that include storms such as hurricanes or even winter storms mm, um, has increased, and also number of droughts and also number of floods. There are a few um, extreme events that recently took place. So the overall takeaway from this slide is that there has been a reverse sort of association or the relationship between the number of um, global trends in disasters versus the number of fatality. Now, which is also seen in the other graph here on the bottom right hand side. You can see in this graph we are looking at number of displaced people since 2007 to 2019, and you can see in relation to various different hazard related disasters, same color as this one, so blue being flood, red being drought, and light yellow being extreme weather events. So so there isn't really a very clear trend. That's because the time frame is much shorter. But what is remarkable here is that you can clearly see that the number of yellow events, which are related to extreme weather events, are on the rise. And so is the number of displacement. So the black line here shows the number of displacement that is also rising over time. Now, climate change, I'm quoting the recent IPCC report, the IPCC being the Intergovernmental Panel on Climate Change, that published very recently the AR6, the Assessment Report 6, where it says that the climate change is bringing multiple different changes, such as floods and droughts in different regions across the world, and all of which will increase with further warming of the Earth's atmosphere. And this particular report, this latest IPCC report, has clearly suggested that the warming of the Earth's atmosphere is now overwhelmingly evident that it is caused by the human. So it is caused by the anthropogenic activities. So the human activities are responsible for the warming of the Earth's atmosphere, which is now bringing us all these different extreme events. So I perhaps spent too much time on this graph, but I think you got some of the ideas, key ideas from this slide. Once again, if you have any questions, please use the chat box to populate your question, to write down your question, and we can come back to it hopefully towards the end of this lecture. Now, let's move on. As I said, in the interest of time, I often tend to digress, so I'll keep it to time. I will be only talking about drought and flood, but particularly I'll focus more on flood in this lecture. So here, just to mention about the global extremes. So one of the extremes is drought. And in this, again, in a global map, we are looking at soil moisture. Because there are several ways you can measure droughts, but normally speaking, drought means less water. Either it's less rainfall or less soil moisture or less surface water or even less groundwater, depending on what kind of drought we are talking about. So drought can range from agricultural drought, meteorological drought to hydrological drought. I'm not going to go into detail. That's perhaps a topic for another lecture, for another time. But just to give you an idea that we are looking at soil moisture in August 2021, and it's taken from surface soil moisture conditions from GRACE FO satellite. Now, I'm going to spend a minute or so to explain GRACE. GRACE stands for Gravity, Recovery, and Climate Experiment. It's a satellite mission managed by NASA in the US and also jointly with the equivalent organization called the DLR in Germany. And you can see here, this little diagram here, this is how you can imagine the two satellites, and they're unofficially known as Tom and Jerry. That's because they, like the cartoon character Tom and Jerry, they chase each other. So the two satellites rotate around the Earth every 90 minutes, and the two of them keep track of the distance between the two at all times. When the two satellites are flying over ocean, where the mass is nearly constant, there is not much change in the difference. But as soon as they start flying over a mountain, then because of the extra mass under the mountain, there is a huge pull from the mass that, because of gravity, it attracts the front satellite from the trailing satellite, and then there is a distance. And by measuring the distance, scientists can actually translate the data in terms of terrestrial water mass changes. And here we are looking at soil moisture change, that is again from the satellite, as well as using the um, land surface model data with the satellite. So it's a combination of Earth observation satellites and models to show that many parts of the world where there is red, you can see high risk of drought. So the droughts, as we speak, are happening in in many parts of the world, including in Brazil, in Western US, in Sudan, in Kazakhstan, and in Myanmar, and also in some part of the Middle East, and also in Madagascar. The south of Madagascar is experiencing drought for a number of years now. So again, just to give you an idea that because of the extreme weather events and the climate change, we are experiencing more and more droughts. I'm going to come back to it, how it relates to the extreme climate events later on in the lecture. So let's move on in the interest of time very quickly. So I'm going to show you this area very quickly. And here we saw that in June and July, because of extreme heat events, extreme heat waves, in the western part of North America, especially in British Columbia province in Canada, and also uh, Oregon and Washington states in the United States, we have seen he, heat dome. So it is basically a mass of hot air that lingered around one particular area for a long time. And surprisingly, some parts of this western North America saw temperature as high as nearly 50 degrees, which is extremely high and extremely unusual for this part of the country. And there has been a lot of death because of the extreme heat waves. And the World Meteorological Organization suggested that the recent heat waves in North America were almost impossible without climate change. So here you go. There is that link between climate change and extreme events happening around the world. Now, as I said, this is not the topic of my lecture. I'm going to focus more on floods. So in the next few slides, I'm going to show you a number of recent flood events. So here in a snapshot, you can see this is from the floodlist.com, which is a nice website for accessing information on recent flood events. And you can see this map is showing that in July alone, over 900 people sadly were killed in flood related disasters across the world. So let's have a look at quite a few of these recent events. So this is um, the latest flood events that happened in New Jersey, USA, that is linked to the Hurricane Ida. Now, Hurricane Ida hit the state of Louisiana on the 29th of August, uh, being nearly being a Category 5, so extremely catastrophic hurricane that made a landfall in the southern part of the country, but actually that carried on through across the country through the most of the northern east northeast part of the country, and then it brought extreme rainfall in some parts of the northeast of the US, particularly the New York state and the New Jersey. And you can see some of the statistics here that 82 million, sorry, not million, 82 millimeter of rainfall fell in New York, in New Jersey in just an hour. Just to give you an idea that 82 millimeter of rainfall actually falls in the city of London in, let's say, in December or January. So it's a month worth of rainfall falling in just a matter of an hour. So that's the sort of extreme weather events we are talking about. And unfortunately, 40 people died in the flood events, and I think across the country, um, the number of fatality is even much greater. I think 82 people altogether sadly died because of this extreme hurricane and associated flooding events. So let's move on to the next example. So this example from Central Europe. So remember in July, there was news everywhere about extreme flooding that took place in Central Europe, namely the countries Germany, Netherlands, and Belgium being the hard hit, also part of Poland. And here, the German weather services recorded more than 150 millimeters of rain in less than 72 hours. So this is a huge amount of rain falling within a very short span, creating catastrophe, and it sadly it killed more than 230 people in Central Europe. So in Germany alone, the fatality was 140, sorry, 184. Sadly, 184 people died because of this um, flood caused by extreme rain events. Moving to another example from China, again at the same similar time. So this is we're looking in August, um, and then the extreme flood events that sh- that that shocked the whole world took place in the Jiangsu, Henan province of China. You can see it in the map here. So this is China, and we're looking at the Henan province in China, where astonishingly high rainfall, so 623 millimeters of rainfall fell just over 24 hours. So this would be the amount of rainfall we see here in London, the southern part of the UK, in 1 year. So that's the rain we're talking about. It's a huge, huge amount of rainfall falling in just a matter of 24 hours or so. So again, the number of fatality there was extremely high, over 300. So now moving to the theory part a little bit, we have seen this series of disaster events, particularly flood-related disasters, taking place all across the world. Now, to understand uh, the risk in terms of the disaster risk reduction sort of language, we can see disaster risk equals hazard times exposure times vulnerability. Now, I'm going to read from the UNDRR General Assessment Report, just to give you some of the um, definition of the terminologies. Now, disaster risk is expressed as the likelihood of loss of life, injury, or destruction and damage from a disaster in a given period of time. So that's in a nutshell. It's a definition taken from the UNDRR Global Assessment Report of 2015. And it equals, of course, there has to be a hazard in order for a disaster risk to be present. So hazard is a process, phenomenon, or human activity that may cause loss of life, injury, or other health impacts, including property damage, social and economical disruptions, and environmental degradation. Okay, so that's hazard. Now, in order for risk to be present, there has to be exposure, right? So there has to be either people or property. So exposure means a situation where people, infrastructure, housing, production, capacities, and other tangible human assets located in a hazard-prone areas. Again, that's taken from the UNDRR terminology 2017. Finally, you have to have vulnerability, which is the trickiest component of hazard disaster risk uh, assessment. And the vulnerability is characteristics determined by physical, social, economic, and environmental factors or processes which increase the sustainability of an individual or a community, assets, or systems to the impacts of hazard. Again, it's taken from the UNDRR terminology 2017. Now, what does climate change is playing a role in this disaster risk? This is taken from the IPCC, a report that was published in in chapter 6. This is not the recent IPCC report. This is the earlier IPCC assessment report 5, and this is a special report on disaster risk reduction. And you can clearly see that the risk is sitting in the middle of this diagram, almost like a propeller, if you think. And there is one arm, there is hazard, there is exposure, and there is vulnerability. Now, as I have as I have given you the terminologies, that identifying hazard is easy. Identifying exposure is perhaps relatively less tricky, but identifying vulnerability, which involves basically the non-climatic drivers that involve socioeconomic processes, such as risk. It involves risk management, climate resilient pathways, and adaptation and mitigations, and social capacity to cope. So lots of other things that is involved. I'm not in the interest of time, I'm not going to go into detail. I'll just try to explain um, the recent events in the context of this disaster risk formulation or formula. So let's have a look. So this is New Jersey. Again, we're looking at a Google Earth satellite image, and here you can see this is New Jersey, and this is the New Brunswick, and this is Somerville, and there is that Samaritan River that flows through here, and it falls into the Atlantic Ocean, and that's before the storm Ida made its landfall. And here you can clearly see that there is that river. Of course, there is flood hazard. There is clearly exposure. Some areas are high exposure because of number of people and buildings. Some areas you have the exposure is much less compared to the other. And then vulnerability, just for the sake of argument, to make this point, I just thought maybe distance to river could be considered as a vulnerability, because that would determine how much time a person will take to kind of get evacuated if there is flooding taking place in the region. So in the simple context of disaster risk, you can clearly see that all of the components are there for a disaster to take place. Now here is after the storm. You can clearly see that the floodplains are obviously flooded, and also people's house and other infrastructure got flooded too. That's because those low-lying areas are actually part of the floodplain. So where does river flow? River flows through the floodplain. So it's people often build their homes and other infrastructure on the floodplains, making them exposed as well as vulnerable to any flooding events. Now, this is a model simulation, but I think I'm a bit running out of time. So I'm going to share the link to this half a minute video simulation. But maybe I can come back and play if I have time towards the end. But again, the simulated flood map basically shows where the areas we have seen flooding to take place. Again, giving you another couple of examples to make the case that risk is a function of hazard, exposure, and vulnerability. So here we are looking at in a flooding event that took place in 2013 in Germany. And here clearly you can see there is that river, which is the source of hazard. You have exposure, some areas high exposed, some areas are population and their infrastructure, their homes are less exposed. This is the other way around. So this is high exposure, this is low exposure. Apologies for the mistake here. And then vulnerability is the distance, and you can clearly see, of course, this is quite a disastrous results. That's because the floodplain got flooded because of extreme flood events. Now I'm going to move to another case, which is the recent case, 2021 flood case in Germany. And we're looking at a meandering river system here, so which is the source of the hazard. You have exposure, so some areas are clearly exposed, highly exposed to flooding risk, and this is the river flowing, our river. And then vulnerability, if you think is the proximity, then look what happened. The result is catastrophic. That's because a river, normally where it flows through the floodplain, and it is basically people who build their houses and homes and other infrastructure and entire town, if you like, on the floodplain. So there was that pre-existing risk there, which because of the extreme flood events recently, it became catastrophic. So we can't really can you really now blame solely on climate change for these disasters? Think for a moment, perhaps not. It's partly because the way we have developed our towns and villages around rivers and floodplains. We have made ourselves vulnerable through increasing exposure and increasing vulnerability. Now, why are you seeing more extreme events today? So uh, before I do that, I'm going to explain in very briefly that we often, there is a dilemma of attribution of climate change to extreme events, and whether it's a weather events or it's a climate change induced extreme weather events. There is the debate. I just wanted to appreciate it full of text. I'm not going to read all of that. It's from climate.gov, which is there is a reading list at the end of my lecture. You can I can refer to that. Basically says that the extreme events related to heat and rainfall are easier to study than extremes related to fires, droughts, or tornadoes, perhaps. So often the attribution is difficult, and it's debatable, but in case of rainfall and heat, it might be a little relatively less complicated. It's easier to attribute to recent extreme events to anthropogenic climate change than the other types of hazards we see. Now, I'm going to talk in the next sort of 5 minutes or so. I'm running a bit slow, but hopefully I can wrap up in the next 10 minutes or so. So here, why are we seeing more climate extremes? Now, climate change, as we know, it manifests itself through mainly changes or intensification, perhaps, in the Earth's hydrological system. There are several components of the global water cycle, the hydrological cycle, that is affected by the warming of the Earth's atmosphere. For instance, we are seeing changing rain and snow pattern because of global warming. We are seeing stronger storms. We are seeing more droughts and wildfires. We are obviously seeing rising sea levels, some of the slow onset natural hazard associated with the anthropogenic global warming and climate change. But in the interest of time, again, I'm just going to focus on one um, component um, of the hydrological cycle, which is rain, and I talk about changing rain fall pattern, particularly the intensification of rainfall that are often the root causes of extreme and flash flooding that we have seen happening globally. So why do global warming and climate change impact water cycles and cause extreme events? We need to understand that. We need to understand um, how water vapor or moisture um, is normally held in air. Well, when I say held, air actually doesn't hold water. So the air, as we know, the air is composed of a number of different gases. So there is nitrogen, there is oxygen, and most of it is actually composed of nitrogen and oxygen. So if you go to the number of molecules present in air, in dry air, it contains 78.08% of nitrogen, 20.95 of oxygen, some argon, some carbon dioxide, and very little water. So about 1% at the sea level and 0.4% over the entire atmosphere. So we're talking about a very tiny proportion of air that is occupied by moisture. Now, warmer air holds more water, meaning if we warm the air, the moisture holding capacity of air increases. That's because if you heat up air, the air particles, the air molecules get energy, and they move around very fast. And as they move around very fast, they don't get condensed very soon, or therefore they don't fall as rainfall. So as you warm up the air more and more, it holds more and more moisture. In that sense, warmer air holds more moisture. What happens is the increased moisture in the atmosphere is driving the shift to heavier and less frequent rainfall. So as you are um, blowing your balloon, with more and more water vapor, at some point the balloon is going to pop. And when it pops, it will pour all of the water. So when it rains, it really pours. And that's the sort of basis of extreme precipitation events taking place under global warming. So there is a very clear scientific basis of that heavy rainfall to happen. And that is because of the exponential relationship between temperature and water vapor. As I said, warmer air holds more moisture. So at 0 degrees C, the air moisture holding capacity is 4.5 grams per cubic meter. The same air, if you heat it up to 30 degrees C, it can hold 70 grams per cubic meter of moisture. It's a huge increase. It's a proportion. It's an exponential increase in the moisture holding capacity of the air. So again, I hold because, as I said, molecules, um, air, the water molecules can really move very fast, and therefore the capacity of holding more moisture increases. And as it falls, it tends to deplete all of its moisture, and therefore we are seeing extreme rainfalls to take place. And the result is 6 to 7% more moisture in the atmosphere for every degree increase in the temperature. So we have already seen from the pre-industrial context, pre-industrial period to now, the global temperature has already increased more than 1 degree C. Therefore, the water cycle, the global hydrological cycle, is now has got now more water than it previously had. So there is more water in the circulation, and therefore when it falls um, as rainfall, it really pours. And also we are seeing more heavy precipitation events causing extreme flash floods in the tropics and subtropical region. But at the same time, in other regions, there is fewer low to medium intensity rainfall, or in some places, no rainfall or no precipitation at all, because it now falls as moderate, heavy to moderate precipitation somewhere else. So there is that disproportionate increase in the heavy rainfall, and some areas are not getting rainfall at all, increasing the risk of drought. Often we see flash drought, which is very similar to flash floods, but it's the opposite when there is very low moisture in the atmosphere in the presence of high temperature. I've got a couple of slides. I'll finish very soon. But now moving towards the idea of resilience, I mentioned that this lecture is to talk about not only risk, but also perhaps what are the key elements of resilience, particularly in relation to fresh water. So here, the title I put is that floods with silver linings, but it comes at cost. So the areas such as here in this satellite image, we're looking at flooding in Somalia. So Shebel River in Somalia under a normal year, you can clearly see there is very little water, or perhaps you can only see the water in river. But this is the whole of the floodplain, which is now flooded in 2018. The whole floodplain got flooded, and actually it created a huge humanitarian catastrophe in the region. It displaced more than 100,000 people because of this catastrophic flooding event. But as I said, floods do have a silver lining, because extreme precipitation and flood events help replenish groundwater in dry areas. So the groundwater, which is sitting underneath our feet in porous sediments and rocks under the Earth's surface, which is actually the largest store of fresh water on Earth. So 97% of fresh water is actually is found in aquifers all around the world. It's the biggest source of fresh water on Earth. Now, groundwater in some dry areas where we are experiencing extreme flood events get replenished very episodically. Whenever we have extreme events, it does help generate huge amount of um, recharge, we call it, or replenishment. And there's a recent paper published in Nature that I co-authored that shows the observed control on resilience of groundwater to climate variability in sub-Saharan Africa. So the takeaway, we in this study, we collated long-term groundwater levels data, and we found that in dry, so semi-arid and arid regions, where the extreme rainfall happens once every few years, that tend to um, fill up the aquifers, the underground, in the subsurface groundwater system very much, and that can sustain for a number of years. So there is that going forward, there is that positive take from the extreme events and climate change is that groundwater to the rescue. So the adaptation for freshwater scarcity, particularly in dry areas where there is very little or lack of fresh surface water, groundwater can be used strategically as a vital resource to buffer droughts or water scarcity. So adaptation climate change is basically means better water management, right? So, and groundwater can actually play a huge role in in the midst of this climate crisis in many parts of the country. I have run out of time almost, but again, perhaps there was too many ideas that I threw um, in this lecture. But I'll be happy to reply to any of your questions you may have, and perhaps start a discussion in the remaining 10 minutes or so. But again, if you are generally interested about water, climate extremes, um, disaster risk assessment in general, um, come and see me or email me. I'll be happy to respond to your questions. So I'm going to stop here with the reading list, and I'm happy to answer to any questions you may have. Um, okay, so I'm going to go back to the, if I stop sharing for a moment and see, do I have anything?